Thanks a lot, and it's been a pleasure to be here. Thanks to the organizers for the opportunity. Thanks for sticking around for the last day as well, for those of you who are leaving, like myself, and I want to apologize in advance that I'll miss the discussion. So if you'd hate the talk, it will not be recorded. You can vent then. Okay, so the question I want to try to answer is, how light can dark matter particles be? Dark matter has revealed itself through its gravitational interactions over, close to a century. Then we asked dark matter, who are you? And it underwent an existential crisis and hasn't responded. So we don't know its mass, charge, or spin. We'd like to know these things. But we've been pretty bad at figuring this out. As you all know, what we know from gravity is the density, mass density of dark matter, not the number density, and hence we don't know the particle mass as well. So this allows a huge range of allowed masses, I would argue between 10 to the minus 19 eV, and for composite particles, even a few solar masses. And apologies to Farah, I should have had a pug here. I will change that in the next slide. Okay, so we don't know what the mass is. However, if we start making some assumptions about these particles, for example, the spin. Let's say I say that it's a fermion. Just one assumption, and suddenly you've narrowed this range enormously. Right? So Pauli exclusion will tell you that dark matter particle masses have to be higher than 100 eV. It's a huge change already. However, if you allow the particles to be bosons, that constraint goes away, and now we are back to this huge range that's available. Especially in the light regime, when particles are much lighter than an EV, what we find is that these particles are sitting on top of each other. The de Broglie wavelengths are overlapping so much that it's natural to think about them as a classical field. Right? So it's in this regime that I want to explore how light can dark matter particles be. So we're going to try to see if we can push that boundary a bit. Before I go into this, I want to start out by saying it's not the number for me that matters, and I hope that's not what you take away from the talk. It's that there is this idea in here that we can push this boundary as time goes on, okay, in the way that I'm going to try to explain. Okay, so the work that I'm basing this talk on was done with Mehrdad Mirbabai at ICTP Trieste. That paper is available. And the numerical simulations that I will show related to that, which is not published yet, are all done by Xiang Ling, who is a graduate student at Rice University. Okay, so here's my two-slide summary. We claim that if dark matter is made up of a field such that the dark matter density is dominated by sub-horizon field modes, then the mass of the dark matter particle has to be heavier than 10 to the minus 19 eV. I know that was a mouthful. But let me sort of tell you in pictures. So imagine dark matter is some scalar field. Here is the power spectrum of the field of dark matter. Notice that it's peaked at some scale. In the early universe, before matter radiation equality, I'm assuming that this is the shape of the field spectrum. For those of you who are more used to thinking about particles, you could also think of this as a phase space distribution, okay, over momentum. So that's another way of thinking. It's a peak momentum in this momentum distribution. I claim that under this one assumption, you essentially get this bound. Okay, so I hope it's relatively general, but of course, as always, I'm not going to use the word model independent, because as soon as you use that word, you're wrong. So it's not model independent, but it's general. Okay? It's general. So here's the argument. If the dark matter density is dominated by sub-Hubble field modes, meaning it's a peaked power spectrum, then it has two phenomenological implications for the dark matter density power spectrum. That's the thing we are trying to talk about and observe, of course. It will lead to an white noise excess in the power spectrum on small scales, and it will also lead to a free streaming suppression. So the first assumption leads to these two effects. So far, we have not seen this in the data, And by data, I'm just generically thinking we know the power spectrum, let's say up to of order 10 megaparsec inverse in wave number. The fact that we haven't seen this is what gives rise to this bound. Okay, so that's the entire argument that I have. I'll of course flesh it out as we go through this. Just as a way of comparison, let me just put up some bounds. I know there are many people here whose bounds I must have missed here. Apologies for that. But this is just to give you a sense of where the numbers are when people are talking about these things. Again, the goal is not to say one bound is better than the other. There are different assumptions going on in here, but just gives you a ballpark of where this bound lies within this context. And you can ask me about this in more detail if you would. So here are the details. Imagine dark matter is a scalar field. For example, it could be axion. It is dark matter, so at some point it better become non-relativistic. So we'll assume it's non-relativistic at some point in the early universe before equality. And this is the energy density of dark matter in terms of the field. In terms of the power spectrum of the field, the average energy density can be written as an integral over the wave numbers or momenta of this field, like this. Okay? And again, let me just remind you that I'm assuming that this what we would call dimensionless power spectrum for delta, here is just Q cubed P phi, this is the variance of the fluctuations, it's peaked at some sub-horizon scale. Let me just contrast it to something perhaps some of you have thought about, which is a type of power spectrum in the field which is scale invariant, meaning most of the power will be roughly in the zero mode of the field. It's a homogeneous field with tiny fluctuations on top. This is not that. This is all the power is in small scales. There's no homogeneous mode of the field. You might wonder, does this model exist? Have people written it down? And I would argue, yes. If you think about dark photon, dark matter, it has this shape of the field spectrum. If you think about scalars produced gravitationally during inflation with significant non-minimal coupling, then it would have this spectrum. If you think about almost any process where you produce dark matter after inflation, not during inflation, but after inflation, for example, from phase transitions, axion-like fields produced from strings, you have parametric resonance converting one field to the other, all of those cases, I believe, will fall under this category, that you will have a peaked spectrum. So it's a very general thing. Notice I've removed one example, and this is the example of a light scalar field minimally coupled during inflation. Typically, that will have a homogeneous mode. Okay, so that's the one thing that my bound doesn't directly apply to. Okay. Let's move from the field to the density. So that was the field power spectrum. Now I'm going to talk about something which we are closer to observations, which is the overdensity power spectrum. If you take this field power spectrum and try to calculate what the density power spectrum is, you will find that there is a universality to it, which is relatively independent of the detailed form of this shape. The universality is that if you go on wave numbers that are small compared to the location of the peak, then it will generically be that of white noise. That means the power spectrum is just a constant, and the k cubed times the power spectrum is just k cubed. Okay, so it's generically white noise. This is quite general, and one way of thinking about it is that if your field, especially if it's produced after inflation, it has a finite correlation length. If it has a finite correlation length, then there is no support beyond some length scale. As a result of which, if you do the Fourier transform of that, that means the 2-point correlation function in position space going to 0 implies in Fourier space that'll be white noise, or a constant power spectrum, which is k cubed. Okay? So that's the argument. So it's quite general. It's just causality, if you want. Okay? The argument that is giving you this k cubed. It's just short noise at the end of the day. Here is a visual picture of this. If you don't think in power spectra and you want to see the actual density fluctuations, here is, if you have this kind of a field spectrum, and if you then try to construct a density power spectrum out of this, then you notice you have some structure on small scales corresponding to the peak. And if you go on scales larger than this structure, it's just Poisson noise. It's just short noise. Okay? And that's what this is why this is k cubed here. You'll say, well, but obviously, dark matter, we've seen a roughly scale invariant spectrum already. We know this very well from large-scale observations. this can't be the whole story, and it isn't. Because if you go to even larger length scales than this k cubed, then at some point you will merge on to the scale invariant bit, roughly scale invariant bit. These are isocurvature on small scales in the sense that they are not correlated with curvature fluctuations on that scale. These are the usual adiabatic ones. Okay, so locally you produce dark matter, it kind of does whatever it wants, but it's still born in potential wells that were created by inflation. So there is a correlation on long wavelength scales, and that's what this part is. So you have the scale invariant bit joining this k cubed bit, which is the isocurvature part, and you can quickly see that if you actually, I'm plotting this cartoon at matter radiation equality, then the amplitude of this flat part roughly around this scale, it's running as a log, so it doesn't change too much here, but it's about 10 to the minus 6 in amplitude. So if you compare with this part and try to find where the intersection is, it's 10 to the minus 6, cube root that, and that's what gives you this location where you deviate from scale invariance, which is about 10 to the minus 2 times the scale right here. So the scale of the peak is this white noise peak, or the scale which was there in the initial field spectrum, roughly. The deviation from scale invariance you'll be able to see on much larger length scales, just because the white noise scale continues down. And that's about a factor of 100 larger length scales. So first thing we should learn is that interesting things were happening here, but we can see the effects on larger length scales, okay, by a factor of 100 already. So when people ask me, or nobody asks me actually, but I will tell you, if you were to ask me, how should you parameterize the shape of the power spectrum on small length scales? My first answer would be the most generic thing I would want, because of these arguments, would be you should have a short noise component at large wave numbers. We haven't seen that yet, but if you want to parameterize and look for it, that would be something we should do. Not just for this model, but more generally as well. Okay, now let's go a little bit further. Okay. Next thing I want to tell you, so first part of this picture that I showed you is that there's this white noise piece and we should look for this break in the spectrum. The next bit is that there's one more effect, again coming from this peaked power spectrum in the field. Remember, if you think of this as in phase space, there is a finite momentum of the particles when they're produced. So this finite momentum also leads to these dark matter particles moving outwards freely after they're produced. It's just free streaming, they're just moving along. And that will try to wipe out structure if it exists, right? So if there is already structure that exists or is being created, it will try to wipe it out, just like free streaming does for warm dark matter. It's the same idea here. The difference here is that this is not warm in the sense of it's thermally produced dark matter. This is non-thermal production of dark matter, but it's warm in the sense that it still has some velocities. Okay. So even non-thermal produced dark matter can have free streaming. This is something that usually people don't think about, but once you think about it, it's not, I hope it's not so complicated to think about that. Okay, so what will this free streaming effect do? Something I've found which will seem counterintuitive, I suspect initially, is that given the assumptions I've made, free streaming will not wipe out the white noise bit at all. It will leave it as it is. It will start wiping out the adiabatic part. So this white noise part will remain as it is. One way of thinking about it is that you have these overdensity fluctuations. Then beyond that length scale of the fluctuations, it's white noise, meaning the correlation is 0. Free streaming can't make a 0 correlation more 0. It's just 0. If I make it negative, there's a correlation now. So that's why, however, there is a correlation already existing because of the adiabatic fluctuation. So that's what free streaming now tries to wipe out. So, and you can calculate what that scale is. This is just how far does your particle travel from the time of production. And you can write a simple formula for the inverse length scale, which is this K free streaming scale. And for simple models, it's just related to this peak in the spectrum K star and the mass of the particle. Why do both scales appear? So previously, it was just K star that determined the white noise break. Why does mass appear? Because free streaming is about velocities, which is momentum K star divided by the mass. Right? So that's why you have both things in here. I can tell you all that, but perhaps, again, visually might be more convincing. So this is a toy simulation. This is a full 3+1 dimensional simulation of the fields. And let me see if it hopefully runs. So I'm running the simulation. You notice the initial spectrum had the isocurvature part and the adiabatic bit put in. Notice as the simulation runs, the power spectrum starts wiping out this scale invariant adiabatic part, but leaves the isocurvature bit intact. So this is what I was arguing for, and that's exactly what you see from full field simulations. In fact, this you can do by, I mean, we did it in the paper by hand. Here it's just for visual purposes. Again, power spectra are great. Perhaps still you want to see it in terms of the field and the densities, what they're doing. What I've done here is I'm plotting the density in my simulation volume. This is a scalar field simulation on lattice. I'm just plotting the overdensity in the field. And just to make sure that this part of the spectrum is visible, I have averaged over one direction of the box, okay, so that you can see the long wavelength mode. Otherwise, it will be buried here. Notice there's a small scale structure here that's coming from the peak, and this long wavelength mode, this large orange, blue, orange part is this part of the spectrum. We will let it run, and both things are running, and because this will take too long, free streaming does take a while, so I'm just going to run it quickly. Notice the mode disappeared. Right, so this is just free streaming wiping out the adiabatic mode. Okay? And this is still happening on the other side. Okay, so hopefully I have somewhat given you something to think about, that, you know, this is something that will happen quite generically. And just repeating the argument, if you have an initial field spectrum that's dominated by sub-Hubble field modes, then you will have two effects here. One is white noise isocurvature fluctuations. This is a causality type argument if you want, although you can, it's actually more general. Even inflationary produced dark matter can have this peak. It's not necessary that you have to do it after inflation. And the free streaming part is just stuff moves. It has initial velocity, it will move. Given that we have not seen these effects, that's what gives me this constraint. Think about it in the following sequence. The deviation is this much. We don't see this, so this deviation must be larger than k observed. That gives me k star being bigger than some value. I use k star being bigger than some value in the second expression, and this also has to be bigger than k observed, and that gives me a constraint on the mass. Okay, so that's how the argument works. And I think it's important for me to point out that we did not need to know what k star is. That's a model-dependent thing. Each model will have different things, but we're just saying we're using observations to tell you what the bound on the mass is by just seeing a lack of these features. For some of you who work on warm dark matter, you might be like, what a ridiculous bound. 10 to the minus 19 eV. We have keV bounds, right? So why is there a difference between the two? The difference is that for warm dark matter, you're making an additional assumption that it's thermally produced, which is to say that the temperature is of order the mass, which tells you that this k star that I was talking about for warm dark matter is much bigger, necessarily will be bigger than typical things that you get for non-thermal production. Thermal production, the temperature is of order mass. Non-thermal production, the Hubble scalar is of order mass. They're related to each other by an M Planck. That's where the difference comes in. So that's why you get much stronger bounds for thermally, or the typical warm dark matter, but for non-thermally produced dark matter that is still a bit warm, you get the bounds that I quoted. So arguably, I think what I'm saying is more general because I've made fewer assumptions. Okay, let me wrap up. The strengths, I hope, are there. I said I would not use the word model independent, but I still put it up here, but that's why in quotes. It's not model independent. Everything has some assumptions in it, but it's relatively general. It doesn't depend upon the spin of the particles. As long as they're bosons, this will work. Okay. It does assume something about the initial fields are relatively free and not bound up, right? They're free to propagate. So that's an assumption that we've made. For those of you who think about fuzzy dark matter, which is the homogeneous mode, as the dominant mode, in that case, the constraints on the mass sometimes come from the Jeans cutoff. If you have free streaming, then the genes cutoff will be a weaker bound than the free streaming bound. You can see it parametrically here. But you need the free streaming, so you need the peak spectrum. Something that is nice that comes out of this analysis, we think, is that the bound on the mass is proportional to the square of the observation scale. So as your observation scales goes from 10 megaparsec to much smaller, for example, we have noticed structure on much smaller length scales, so that will improve this bound rapidly. Okay? Just upcoming, we are going to put this a little bit into effect by using Milky Way satellites with Ethan and Risa. I've used the numbers from Lyman Alpha. This will hopefully change things, but there are some subtleties there. If you're interested in the simulations and how to use them, also let me know. Xiang is working on this at the moment. Here is very quickly, I know I'm out of time, but I will, in cosmological perturbation theory, when we do the early universe and we think about, okay, what happens to adiabatic fluctuations as they enter the horizon? They get a boost, right, in the radiation dominated area. This is Hu and Sugiyama telling us this from 1990s. Here is a full field theory simulation also showing that boost when things enter the horizon, and they boost by the correct amount. And then after the initial boost, you get free streaming wiping out that boost also. Right? So both of those things are taking place. So it's nice to see. Here is, again, a visualization of that. The first part of the simulation is in actual time, meaning reasonable time this one is sped up, meaning I've sped the frame rates up very quickly. And you see the free streaming here, because it just takes a long time to see this. Okay, let me end here and say that this way of thinking that even if you have non-thermal production, you should have these effects that we should look at, and that can give you a relatively general bound. I also want to echo what was said yesterday, that, bound good, detection better. All right, so bounds are all nice and wonderful, but we should aim for detection. And these features are things we can look for. Right? It's not just about not seeing them. We should look for these, and if we see them, it will tell us something about the production mechanism that was there. Thanks a lot.